Good morning, everyone. Morning. Thank you for coming. My name is Stefano, and I'm part of the serverless organization at AWS. As you can imagine from the title here, I spend a lot of my time working with AWS customers, building Java applications on Lambda. How many of you here are Java developers and have worked with Lambda? Quite a few, OK. So, cold starts. Let's get going. This is the structure of the session. First, I said cold start. We need to answer this question. Should we even serverless with Java? Does it make sense, given that we're running quite a few challenges with the cold starts? You can guess that my answer is yes, because otherwise we would not be here. And so next, I'm going to tell you a little story, a story of how I went about optimizing the cold starts for a Lambda function. And I'm not telling you the story just because it's more entertaining than me just regurgitating advice at you, but also because I hope to inspire you to continue the investigation yourself and find the next set of tips and tricks. At the end, I'll just give you a quick recap of all of my recommendations. And then we'll look at where to go next, what technologies are coming up to help us and make Java a good citizen of the serverless ecosystem. So let's get going. Let's answer the first question. Should we even serverless with Java? I like to quote Tim Bray normally. If you don't know Tim, he's a distinguished engineer at AWS, super smart guy in general. And he's rightly skeptical of Java's citizenship in the serverless world because of the well-advertised cold start issues. However, he also says that there's a lot of smart people trying to make things better. I am not one of those smart people. I'm just here to relay their messages. And the fact is that cold starts for Java in Lambda can be slow. And you'll notice that in this slide, I've highlighted can be rather than slow. And that is because there's a lot that we can do to make it better. And we'll go through all of those tips. And another answer to that question on whether we should use Java or not is the fact that Java is here to stay. Like, whether we like it or not, 41% of Stack Overflow developer survey respondents use Java, still the #1 language in the TOB index. We need to make it work. And when I say we, I mean all of us. Us at AWS, we will keep chipping away at the cold starts, and we will keep working behind the scenes to make it better. But I'm here to tell you that you are a key part of the equation too, both as application developers and perhaps framework developers. We need to change the way we write Java code to make it work well in Lambda. And so let's get straight into it. Let's see how we need to change that. How many of you here carry a pager and are on call? Quite a few. So this story might resonate. It begins like all good developer stories do, with a pager going off at 3 a.m. My pager specifically. So I get out of bed, bleary-eyed, open my laptop, and go and look at what happened. What happened is that a customer had published an API that used API Gateway and Lambda. And as they start hitting production-level traffic, they hit a cold start challenge. Their 99th percentile latency was 24 seconds, and their max, their P100, was over 30 seconds. That in turn meant that API Gateway was timing out. Not a good experience for their customers, and that pain was quickly transferred up the chain to where it reached me. So the first thing we want to do is put a Band-Aid on it. Just try and make it a little bit better. Buy ourselves some time to go and investigate what happened. And this is the classic Band-Aid. You've probably read about this everywhere. Lambda allocates an amount of CPU to the function that is proportional to the memory you configure. So dial up the memory a little bit. Function gets more CPU. The JVM gets more CPU to play with. It'll start faster. Still very slow, but at least we don't get the timeouts. We've bought ourselves some time. We doused that dumpster fire for a bit, and we can go and investigate. So let's dive deeper. And we have 3 objectives as we do this. Obviously, timeouts have got to go. Ideally, stretch goal for ourselves, we want to get below 10 seconds in cold start time to the P100. And finally, once we have that, we want to sit back and think about what's the right long-term solution. Should we serverless with Java? And by the way, we want to do all of this with the original memory allocation, not the higher one we temporarily set, because that translates into higher cost. So diving deeper, the first thing I did was replicate the customer's application. The replication was very, very simple. API gateway passed the proxy event to Lambda. In Lambda, they used Juice to inject a DynamoDB client, and they pretty much put the event as it came into a DynamoDB table. Their application had a little bit more business logic in it, but for all intents and purposes, this is all I needed to replicate their environment. So I built it, deployed it, and ran a quick load test. I used a tool called Gatling, and I ran a 60-second load test with 50 concurrent users. And this is the output of the Gatling report. You can kind of see what happened there. The P99 and below were decently fast and, more importantly, consistent. So I was happy with that. And in my case, because the load test was so short, just 60 seconds, cold starts didn't have time to seep into the P99. They were just in the max. But they were there, and they were very, very cold. That was about 20 seconds. So bad news because, well, we have a 20-second cold start, but good news because I've replicated the issue. I see the exact same thing that the customer was seeing. So where do we go from here? We replicated the issue, but we need to figure out where it's happening exactly. So the next thing I did was instrument all my code with X-ray, creating subsegments. X-ray is our distributed tracing system, and it allows us to see a breakdown of the execution of the Lambda function. So I ran my load test again, very similar results, slightly slower because I was doing a lot of X-ray work in there. But now I can go to the X-ray console and look at a trace of that execution. This is what I saw. And after I looked at this, I went and got myself some coffee and looked at it again. Do you notice anything weird about this? Took me a little bit to see. First, we have the initialization step. This is where we start the JVM and start the Lambda runtime. That was about 330 milliseconds. Figure it might be go up to 400, but was well within acceptable limits. Next, I looked at where I thought I was going to spend most of my time. In all of those subsegments I had instrumented inside the handler. But what I noticed after a while was this. What is that 7-second gap between the initialization and my handler actually executing? So that was the mystery, the first mystery I wanted to solve. And the first thing I did was try and replicate and check if the JVM was doing OK. Now, first, try and blame Lambda in the JVM before I blame my code. And so I built a very simple hello world function, just one class, returned hello world. And I ran it in Lambda, and the total execution was 87 milliseconds. Can't really blame Lambda or the JVM for this. So my next step, or my best guess, was let's start looking at the dependencies and pull them in one by one into this hello world function to see if they were to blame. The first thing I did was include the AWS SDK for Java. I just included the SDK and created a DynamoDB client. I just instantiated the client. I didn't actually make any call to Dynamo. I just created an instance of the client. And I went and tested again. Well, and sure enough, I'm starting in 6.3 seconds now. And obviously, the package it's gotten a little bit bigger because there's a lot of code from the SDK, but the size of the code doesn't make that much of a difference. Very often, the code is cached where we're running it, and even downloading it, I have quite a bit of bandwidth. You'll have to upload a very big code package for it to have a significant impact on your cold start. And so now that I see this, I have a hypothesis. Perhaps we're loading too many classes. That's just my guess. Like I said, package size is not significant, but the JVM lazily loads classes as it sees them. As it loads your class, it goes and looks at all the dependencies and links them in and brings them into memory. So maybe that's what's happening. When I start a Dynamo client, it's just going and finding a lot of classes. So I wanted to figure out how many classes exactly I was dealing with, whether there was anything to my hypothesis. So I just added a main method and ran the function in local with that verbose class parameter. The JVM would just log loaded class, loaded class, loaded class, so I could go and count it. Now, my guess at the time, with half a cup of coffee in me, was that to receive an event and inject with juice a DynamoDB client and then make a put request to Dynamo, it would take about 100, 200 classes. That was my guess. Do you guys want to take a bet? How many classes do you think it takes to receive an event, inject a DynamoDB client, and make a put? 5,000. Pretty close. It was 4,130 classes. So maybe there is something to it. Maybe we are asking the JVM to load too many classes in a small environment like Lambda. So that wasn't enough. I mean, it's a high number. It's good to know. But I needed to find out who my culprits were. So I ran the command again with just a bit more sorting and uniqueness. And here's my main offenders. It's the AWS SDK. Both the Apache HTTP and Jackson are dependencies of the AWS SDK. Second one is Juice. So the first thing we want to address is the AWS SDK. Before we do that, though, I want to take a quick intermission to tell you what a cold start is, what happens inside the sandbox during a cold start. And I want you to keep this in mind because we will reuse this concept throughout the talk. There's 3 steps to a cold start. We start the JVM, and the JVM loads the Lambda runtime. The Lambda runtime is just a small collection of classes. All they do is use reflection to go and find the class you've indicated as your handler, create a singleton instance of it, and then call the handler method. This is all very straightforward. It's how we would have built it ourselves. There's nothing strange about this. What's important, though, is that during those first 2 steps, up to the point where we have created a singleton instance of your handler class, we have access to more of the host CPU than you do during the function, because we want the functions to start faster. Once that's done, and we get to call in the handler, then the CPU access is throttled to the amount that is proportional to the memory allocated. We'll reuse this throughout the talk. So back to our story. AWS SDK was my first problem child. So the first thing I did was try and switch to the SDK v2. We released the SDK v2 after Lambda was released, and what that means is that the team that built it had Lambda in mind as well. And there's 2 main benefits to it. One is a lot more modular, meaning the package size is going to be a lot smaller because you can include exactly what you need. But more importantly, it allows you to pick the HTTP client that you want to use. And that takes care of my Apache dependency there. And I would argue that if you're working with Lambda, the good old-fashioned URL connection client is probably the right one to use. And that is because Lambda itself will enforce that each sandbox processes 1 event at a time. So unless out of 1 event you need to make 50 concurrent HTTP requests to a downstream service, you're not really taking advantage of the complexity in the Apache or Netty non-blocking I/O client. Might as well go with the basic URL connection. It's smart enough to reuse connections behind the scenes by itself. So I made the change to my hello world function. Very easy, just included SDK v2, initialized the DynamoDB client, ran it again. Sure enough, there's a 26% improvement. However, package size has gone up. And that is because I discovered that the SDK v2 by itself includes both Netty and Apache. And so I went back and explicitly excluded them from my POM file, pulled them in, package size has gone down, and we found another 15%, which is quite a lot compared to how much the package size has gone down. And that is because behind the scenes, the SDK is still attempting to initialize the other clients, so they are doing some work. So the changes were very simple. Just include SDK v2, explicitly exclude the 2 dependencies, pull in the URL connection client. I took these and I made the same changes to my application, to the one that replicated the customer. Tested again, and I saw consistent improvements. We're down by 30%. We've gone from 23 to 17, still way above what we want to be, but we're moving in the right direction. And more importantly, I went back to the X-ray data, and the gap was gone. I was going straight from initialization to handler call now. So now that we've addressed that first issue, that 7 seconds gap I had there, it's time to start thinking about that initialization step, that CPU burst I get, and try and make the most of it. So that was my next thing. New cup of coffee, make the most of the init time. I was doing all of the work to create the juice injector and inject the DynamoDB client inside the handler method. Obviously, I had declared the DynamoDB client as a singleton for injection, so they would keep reusing the same instance. But nevertheless, all that work was happening while the CPU was throttled. So it's time to shift that around and pre-configure components in advance. Everything I knew I would need for every single invocation happens during that CPU burst. It means it happens while the JVM initializes the class. In my case, I simply move those out of the handle method into some static class members, just fields, and initialize them there and then. That would mean the JVM would load them as it loads my class, so as the Lambda runtime loads my class, and therefore during the CPU burst. Another change I made was specifying all of the configuration values for the SDK. I own the environment, I'm deploying the code, so I kind of know what the configuration is, where I'm running, which region, which service I'm talking to. And I'm doing this because behind the scenes, if I just said new DynamoDB client or just builder build, the SDK does quite a lot of work to go and discover all the various components. For example, credentials provider. There's a few implementations of the credentials provider interface. They can come from the credentials file in your home directory. They could come from environment variables. They could come from an instant metadata. I own the environment. I know where they're coming from. I'm in Lambda. They're coming from environment variables. So just tell it directly. Same story for region. I know what I'm running. And even more importantly, the endpoint. If you initialize the SDK without specifying the endpoint, it parses a very big JSON file that contains all endpoints for all services in all regions. That's quite a bit of work we're doing there. And it uses Jackson again, which will slow you down even further. So you know it, you don't have to hard code it, place it in an environment variable, but nevertheless, specify it. Made these changes, ran it again, went back to X-ray, and we found another 30%. We've gone from 18 to 12, above our stretch goal, but 18 to 12. And that is because all of those heavy operations, such as initializing juice and the SDK, happen during that init time, where I have more CPU. And you can see that the init time has gone longer, 2.1 seconds compared to the 400 milliseconds where we were before. However, those operations took 8 seconds when the CPU was throttled inside the handler. So we traded 8 seconds for 1.7, and it's a good deal. I'll take it. So before we go into another intermission and deep dive, just quick recap. All I've done is 3 super simple changes. Use the AWS SDK v2. I started front-loading all of the classes that I know I would need every single time. And I provided all known configuration values. And just with that, we made almost 50%. We reduced the cold start time by almost 50%. So next, a quick interruption on why static fields, why I want to use static fields. How many of you enjoy, during your time off, reading the JVM specifications? Neither do I. But this is what it's a very summarized version of what the JVM does when it loads a class. Prepare, so it allocates the memory for all of your objects and fields. Then it links, which means it goes and finds all the other types you're using and loads all of those classes into memory, and finally gets to the initialization step, where it's actually running your code and initializing it. And this initialization step works this way. First, it will run static initializers. That could be static variables that you're initializing there, or static blocks. Then it will run instance initializers, which are non-static variables and blocks in the class. And it will run them in the exact same order in which they are declared. And then obviously after all of this, we get to the constructor. So if you want to get really into it, this is what the bytecode looks like of a class file that uses static initializer. You see there's a special static section there. And the JVM will go straight to it and start executing that code. And the primary difference is that I'm not doing those. I'm not doing the A-load, and I'm not doing the generic object init call. Now, in my case, the class was so simple that those would have been nanoseconds. It wouldn't have mattered. But if you have a more complex constructor and you do other operations inside the constructor, that will take quite a bit of time before you actually start creating the things that are important for your Lambda execution. And that's why I went for static fields. It would be a lot more idiomatic to Java to use the constructor. And I did, and it didn't make that much of a difference in my case. However, as I was preparing this session, I also noticed that the code with the constructor and the fields wouldn't fit in the slide. So we keep the static fields. Either way is fine. It's just whatever makes the code more maintainable for you. Let's get back to the story. So like we said, we had made almost 50% difference just with those 3 simple changes. However, we're still above our stretch goal of 10 seconds. So let's gather a bit more data. I had a main method in my app, so I reran it in local with a profiler. You can use Visual VM, you can use any Java instrumentation. And this is the summary of what I saw. These were the slowest methods. Put item to Dynamo. It was slow, not as slow as the others, and it was the first call to Dynamo. Could have been TLS entry, could have been a lot of things. I'm going to put it aside for a second, and we'll get back to it. Oh, we'll get back to it. Let's instead focus on Juice. Juice was taking a long time to initialize itself. It was taking a long time to discover the class it needed to inject, and it was taking a long time to discover the constructor it wanted to use of that class. And so that brings me to the next hypothesis. Reflection is what done it. And reflection is a super powerful tool. Now, don't get me wrong. I'm not slagging reflection in any way. However, we've become extremely dependent on it as Java developers, particularly the frameworks we use. And while it's amazing, it feels like magic to us that we can just annotate things and it'll go find them, it has its drawbacks. When you use reflection, the JVM cannot optimize the code. It cannot inline code. And if you're not familiar with what reflection is, the basic example is class loader for name. And because that for name is a variable, the JVM cannot know what the value of that variable is going to be in advance. So it cannot inline code or optimize how it loads things. On top of that, because we don't know which class we're going to load, the JVM is going to have to do a lot of class path scanning to go and find that class. And normally, when we run on a big, chunky server, it doesn't really matter. But in a constrained environment such as Lambda, those operations are expensive. So let's go and get rid of reflection. The first obvious thing was switching dependency injection mechanism. I switched from Juice to Dagger 2. They're both Google frameworks. Dagger 2 is a fork of Square's original Dagger framework. And the key difference is that Dagger 2 generates code at compile time, rather than using reflection to find your objects to inject. It uses annotation processors to do that. So let's make these changes and have a go and see what the difference is. Using Dagger was super simple. Just include the Dagger runtime library as well as the compiler package. Compiler is where the annotation processors live. You should exclude it from your deployment package. And then it was a couple of quick changes to my code just to start using the Java standard inject annotations. I had to compile it once for that Dagger database service to be generated. But then I could use it and write code just as you would. If you notice, these are screenshots from IntelliJ. Now, I had to compile it once manually because it was 5 a.m. I had only so much coffee in me, and so I was just in anger typing MVN package. Dagger has a lot of IDE plugins that you can use that will just make this happen behind the scenes, so you don't have to worry about that. But I made these changes, went to test, and we found another 3 seconds. We're down to below 10, but nowhere near what I expected. I expected the gain to be much, much more significant. Went back to the logs, and sure enough, the initialization time had gone from 2.1 seconds back to 400 milliseconds, which means that injection I was doing at the beginning using Dagger was way faster than using Juice. And the rest of the time was spent in the DynamoDB put item call. So it was time to get back to that one. I had ignored it for too long. And at this time, it was late enough in the morning. It was about 6 a.m. I had done enough tries that I felt like sharing the pain, so I paged in the SDK guys to ask them what was going on. Well, what was going on is that the AWS SDK lazily loads its marshallers for requests and responses, as well as errors. And what that means is that all of the Jackson object mappers creation, or object readers and object writers, was happening while the CPU was throttled inside my handler. So I was kind of onto something. It was reflection, but it was the SDK's behavior that was causing it. So we want to move this. We want this to happen when the CPU is not throttled during the init time. Again, trade some of that handler time for init time. And I did something pretty bad, but I did what I had to do to make it work at a time. And I added a static block with a call to DynamoDB I knew would fail because I wasn't specifying a pet ID. However, just the fact that I was making that call forced the SDK to exercise all its marshallers because I was trying. So I went back to test again with this. The handler running 1 second. I got very excited when I saw this. I thought I was the winner. However, the Lambda console only reports the handler execution time. To get the actual full execution time, you have to go back to X-ray. And that time was actually 5 seconds. Not bad. We're well within our stretch goal of 10 seconds. And again, we've just traded handler execution time for init time. Now, it's a very good trick, and you'll be tempted to use it a lot. Keep in mind that you have a 10 seconds limit to it. If your initialization step doesn't return control to Lambda within 10 seconds, Lambda will assume that you're dead and just kill you and start again. So use it, make the most of it, because it's super helpful, but be careful and test it properly. You don't want to exceed those 10 seconds. And so we made a decent difference. This is something that the customer could do very, very quickly. Like, it's simple code changes, swap around a couple of dependencies. Their function was simple, so I'd say we bought ourselves some more time to start thinking on the next step. What's the right thing to do long term? But before we go there, let's rant a little bit more about reflection. How many of you rely on reflection in your work on a daily basis? Cool, quite a few. And is that because you use Spring? How many Spring developers here? No, you're lying to me, there's more. Don't be ashamed, raise your hand. Spring uses reflection a lot. And don't get me wrong, Spring is a great library. Like, I'm not complaining about Spring, but it does rely on reflection super heavily. And I went to check when I was looking at the Stack Overflow developer survey numbers. And it turns out that 99.7% of Java developers who work at companies with more than 1,000 employees are also Spring developers. And that number surprised me, and that's why I said, you're lying to me. Somebody here is ashamed of using Spring. But more than that, a few weeks later, I was having a few issues with Spring. It was just changing the case of a URI before passing it to me. And so I went to Google, like all good developers do, and started searching for it. I expected to find an issue reported somewhere. Instead, the top result was somebody on Stack Overflow asking, how do I change a string to camel case with Spring? Not with Java, but Spring. And that's why now I talk about Spring developers rather than Java developers. It is that pervasive. And we need to be careful. Anyway, back to reflection. How many of you are familiar with how reflection works behind the scenes when you're invoking a method? It all comes through that method accessor interface. That's how Java invokes a method. And as you can see, a very simple test there. Invoking a method is through reflection rather than using a direct access is roughly twice as slow. Now, why is that? There's two implementations of that method accessor interface. The first one is the native method accessor. This one uses the Java native interfaces, the JNIs. What that means is that the JDK inside your JVM space is taking your call and going off to the JVM itself, to the native code inside the JVM, asking it to go and call that method. And trampolining that way across memory spaces means that there's a lot of stacks to be copied around for the calls to happen. If you're passing a lot of parameters, or large parameters, complex objects, that will become even slower. Now, the JVM people are very, very smart, and they saw that issue, and they fixed it, and they fixed it since Java 1.4. And that's why we introduced the generated method accessor. Basically, if the JVM sees you using reflection to call the same method multiple times, I believe the default threshold is 15, it will generate the Java bytecode for the method accessor for that particular method, so it doesn't have to trampoline around between JVM space and native space. However, generating code takes time. Generated code takes memory. So neither one is perfect. On servers, great. Cold start time doesn't matter as much, and normally you have memory to spare and CPU cycles to spare. In Lambda, I don't think there's a good solution either way. On the one side, native method accessor, there's a lot of CPU operations, just instructions to copy stacks around. If you want to generate the method accessor, well then, CPU to generate the bytecode, more memory to load it, and more memory means more cost. So there isn't a great solution to it. Nevertheless, we've gotten down to 5 seconds. And that was as far as I went with the regular Lambda runtime, the Java runtime. So before we go into the what's next piece, let's just summarize everything I changed. We preloaded all of the classes. Everything that I knew I would need for every single invocation happens during the init step, be it static class member and initialize it as static, or put in the constructor. Avoid reflection, if you can. And I know that it's almost impossible nowadays, because most likely your dependencies will rely on reflection somewhere. However, at least try to avoid it in your code, and if you can, pick a dependency that doesn't use reflection. And remember that each class is more bytecode to load. It's more CPU and memory. And this is to keep in mind for dependencies as well. And finally, don't be afraid to get a little bit hacky and prime dependencies like I did with the DynamoDB call that failed. And if you're a Java application developer or a framework developer, please think hard before you create another class. If your constructor just takes one parameter, you don't need a builder for it. No need for a builder class. If you're declaring an interface, because you know you will have one implementation of it, and maybe, possibly 5 years down the line, there will be a second one, just don't create the interface, just declare the class. And if you design your API as well, it will be relatively easy to turn that into an interface when it's time to build that second implementation. So as you write Java code, stop and think hard. Every time you're about to right-click and say new class, think hard whether you need it or not. This is true for Lambda. It's true in general. I think the more classes, the harder it will be for the new developer on the team to absorb your code and figure out how the system is operating. So back to what's next. 5 seconds. It's a good improvement considering that we started from 23. Not great. Avoiding reflection is hard. It's really hard. We spent decades writing code that was super easy for you to integrate with. It looked like magic from the outside, and it's because it relied so heavily on reflection. And I would think that the ecosystem is not going to change, not anytime soon. So it's important that we at least do our part and adjust and change the way we do things. And if you are willing to at least entertain the possibility of changing the way you do things, then we can talk about what's next. Where did I go with my experiment next? Well, like Tim said, there's a lot of smart people working on this problem. And there's a lot of new frameworks and tools that have come out to help with this. They didn't exactly have Lambda in mind, but they were working on the startup time of Java. And I would argue that regardless of whether you use Lambda or you use Kubernetes or whatever it is, cold start time for for Java applications will start to matter, because you use containers so that you can beam pack more and get more utilization out of your infrastructure. And as your traffic spikes, if you take 10 seconds to start, I may have to start 4 containers to handle that traffic. Just because one is still starting, I need more for the incoming traffic. And that's wasted utilization. So this is true, I think, across the board as we move in that direction. And what are these tools? I'm highlighting 3 here: GraalVM, Micronaut, and Quarkus. How many of you have heard of GraalVM? You can take the picture and then raise your hand. It's OK. Not a lot. So GraalVM is a project, an open source project out of Oracle Labs. It's a polyglot virtual machine. It's very interesting. It allows you to run multiple languages alongside one another. See JavaScript, Python, JVM-based languages, or LLVM-based languages. And it allows these languages to interoperate with one another, to call each other, which is awesome. However, that's not why we're here. We're here because GraalVM can compile Java code to a native executable. And it does that by starting your application as it compiles it. It builds its abstract syntax tree, goes and finds both the execution path and the data flow path, and then takes a snapshot of that heap that is created as it started your application. The snapshot of the heap is placed in the data section of your ELF file. I'm not sure how much you want to go into ELF files, but then compiles your Java code as a native executable. And what that means is that when you go to start it, all that application has to do is read that data into the data section of its ELF file and bring it up into memory, and it's up and running. One thing that's worth mentioning, though, and we were talking about this earlier with a few of you, is that, yes, Java code can be slow to start, but the JVM is very, very fast. The server compiler inside the hotspot JVM, the compiler that does runtime optimizations on your code, is really good. When you compile code with GraalVM to a native executable, you'll get an awesome start time, but in warm invocation at runtime, it'll actually be slower than the JVM itself, because the JVM itself can keep optimizing your code to fit your usage pattern, whereas GraalVM is left to speculate what the execution path will be and how you will use it and optimize that way. Now, all is not lost. The GraalVM team is very, very smart. One of the features they're working on, which I think is super cool, is called profile-guided optimizations. What that means is that you'll be able to run your application inside GraalVM as a virtual machine. And as it runs, GraalVM will collect profiling information of how you move through your code, and it will spit out a file with that profiling information. You can then feed that file back into the ahead-of-time compiler so that it can perform better optimizations. It's not left to speculate. It actually knows how your code operates. So this is a super cool project. You should check it out, and I have a few links for you to get you going. And next is Quarkus and Micronaut. These are 2 full-stack frameworks. And what I mean by full-stack frameworks is that, similarly to Spring, they support dependency injection. They allow you to create APIs and can deal with data sources. And they have their own flavor of annotation. But more importantly, they don't rely on reflection. They generate code at compile time. Because the one thing I forgot to mention is that GraalVM native compilation does not support reflection. So you have to either generate code or provide it with a configuration file that tells it where to find the classes you'll want. And here I might hear a groan saying, I'm a Spring developer, you're telling me about new frameworks. I'm never going to rewrite my 10,000 Spring applications just for this. Well, the good news is that both these frameworks support Spring's annotations. So they have the annotation processors necessary to read your Spring Boot application annotation and request mapping, et cetera, and compile it to a native executable. And that's what I did. I actually used a simple pet store sample app we have it was written with Spring Boot, and instead compiled it with Micronaut. And I'll show you that, but do you want to guess what the cold start was for this one? As a native executable running in a custom runtime in Lambda. And this was a full Spring Boot application. I didn't sacrifice anything. I had configuration and beans and auto-wired stuff. So to summarize, and that link is where you can find the code sample. And I have a quick demo that will guide you through it. But to summarize my feelings is that, yeah, like I said, we're not getting away from Java. Java is here to stay. And there is hope yet. That 650 milliseconds cold start time, I think, is well within reason. These technologies are relatively new, but they're evolving fast, and the teams that build them are super responsive on GitHub. So if you run into any issues, they're very, very happy to help you. And if you are a diehard Spring developer, I know that Spring Boot is building native support for GraalVM, so they'll be able to compile Spring Boot applications as native executables themselves. So adjust the way you write code and keep experimenting with these tools. I think there's a future for us. We don't have to go extinct yet. Now I want to show you that sample application with a cold start. I'm old and grumpy. I've done way too many live demos at conferences over the Wi-Fi, so I recorded a video instead this time. I don't like failing on stage. I've done that enough. So let me talk you through. Oh, there's no video? Wow. I can probably play it from my laptop. And I made the video not to fail on stage. Nice, we got it going. Okay, excellent. This is the sample application I linked to. As you can see, it's a Spring Boot application. Nothing too clever about it. I have my controller that uses the standard Spring annotations, the request mapping. I have some auto-wired configuration, and some beans declared in the config class. This is actually an older version of the code. The one you find on the repo is a lot cleverer. I wasn't doing quite as many bad things with the beans and the auto-config, but nevertheless, it's plain Java, just like you're used to writing it with Spring. Where the magic comes in the execution, is at the build time. So I have a Gradle build. It's exactly the same as a Spring Boot application Gradle build. You see it inherits from the Spring Boot project. However, all of the annotation processors are coming from Micronaut, from the Micronaut framework. And that includes the processors that recognize the Spring Boot application annotations. And this build will run, and it will create a fat jar, just like you would in your regular build. And then we go to Docker to build a native executable. And that is because it's a native executable, so we need to build it for the correct platform, the Lambda platform, the Amazon Linux version that's running in Lambda. So run the Gradle build, create a fat jar, and then run my Docker file. I simply start from the Amazon Linux version that Lambda runs, and install all the compiler tools, the developer tools, and the, well, I can actually see when which one is skipped this version? Is it this one? Yes. Thank you. And then we run the build script. This just runs the native image tool. That's part of GraalVM. And you can see I passed the fat jar as a parameter. So let's go and run this build. Go to my dev box, because as you see, my laptop is a 12-inch MacBook. It doesn't do well with compilers. Build a fat jar with Gradle. This is the same build process you regularly run through with Java. And then we get into the GraalVM steps. This video will zoom in and out a little bit, not just because I want to give you labyrinthitis, but because some bits you already know, Gradle build, whereas this is the actual GraalVM compilation. It's not fast. You'll see it takes about 2-3 minutes to build this application. However, trading 2-3 minutes in compile time is well worth the 600 milliseconds cold start time. So this is where it's finding all the classes and creating the heap snapshot. Now, CloudFormation deploy, I use a SAM template. If you're not familiar with SAM, it's serverless application model, just like CloudFormation. So upload my code to the S3 bucket and then call CloudFormation deploy on that. I just wanted to show you that I remember all of the options in the AWS CLI by memory. And so this will go and deploy my stack. My stack includes a Lambda function and an API gateway endpoint. The deployment spits out as an output the endpoint I want to call with API gateway. So once I'm done with this, I will make a simple timed curl to that endpoint. That is just deployed. This will be a cold start as perceived from the client, because I'm running it in the EC2 instance from a client. So that was my time curl. That was a cold start. And perceived from the client was 730 milliseconds, something like that, and full Spring Boot application. So I would seriously recommend, if you are serious and you want to continue using Java with Lambda, go and take a look at these. Go to that link and try that demo yourself. All of the build scripts are there, and you can just run them. Now let's see if I can switch back to the other display without breaking anything. Yes, I can. These are other super interesting sessions about serverless. If you get a chance, go check them out, because there's a lot to be learned. Otherwise, I want to thank you all for your time. Keep in touch. If you're trying these demos and you run into issues or you want to learn more, reach out to me.